Okay, good day, friends. I hope that you are doing well, and let's continue to solve problems on conservation of momentum and impulse. So the problem goes like this. At the moment of closest approach during an elastic collision, the velocities of the bodies are equal to v. What are the velocities after the collision if they were moving along the same straight line with speeds v1 and v2? So the meaning of this problem is something like this. You have two identical balls, let's say, yeah, of the same mass, and velocities v1 and v2. And then at a certain moment, the velocity comes to the same value. At a certain point, yeah, maybe in the middle of the process. But after, again, they would separate from each other, and then the velocities would be different once again. So to imagine it, it would be something like this. Imagine that this first ball is faster than the second ball, but the second ball was moving ahead of this first ball, so its velocity is smaller. It's just 5 meters per second, and its velocity is something like 7 meters per second. And we know that at a certain point, that this first ball catches up to the second ball, right? And when it catches up, it does not just transfers its velocity straight up. Yeah, what happens at some certain point? That let's say, just imagine that they just change their velocities with each other. Yeah, just let's imagine that at the end this takes 5 meters per second. This would be 7 meters per second. Yeah, because the first ball just pushes the second ball, but the second ball pushes this first ball back. That's why its velocity gets lower, but its velocity gets higher, right? But the problem to it, this is not the most important part. The most important part is the middle one. So what happens? What is the meaning of this situation? The meaning of the situation that these two balls do not instantly change their velocities. They do not just transfer their velocities to each other. No, at a certain small fraction of time, they both have the velocity of 6 meters per second, just for example. Yeah, I'm not saying that it is so. Just for example, to imagine. Yeah, because when it hits the second ball, when the first one hits the second one, it has to accelerate, right? And the second one has to decelerate. And when the first one goes up to 7 meters per second and the first one goes to 5 meters per second, then at a certain point, both of them have the same velocity of 6 meters per second, because one of them is accelerating, the second one is decelerating. And at a certain point, they match up their velocities. And as you can see, it is set here at the moment of closest approach, right? Okay, this is just for imagination. I'm not saying that it would be so, and we cannot say that just V3 and V4, they would be just, again, the same values as V1 and V2. No, instead, let's try to think physically. Okay, let me take it a little bit lower, maybe here, and make some analysis. Okay, this problem might look easy, but there is something very interesting to note. What we are going to do is something like this. Let's say we have conservation of momentum in here, conservation of momentum in here, and also momentum in here. This is momentum, yeah, sum of momentums in here, and sum of momentums in here. And in terms of physics, these all can be equal to each other, yeah? Momentum can be conserved at any point. But when we talk about conservation of energy, yeah, conservation of energy and energy here, yeah, let me write it just energy, and also maybe some energy here, this is not conserved, yeah. Instead, let me write it a little bit better. This energy would not match these two energies. These two can match up to each other, but this one cannot match up to this one and this one. Okay, what is the problem about it? The problem is that when those two collide with each other, yeah, at a small fraction of time, those two balls would have some deformation, yeah, maybe not heat loss, maybe, but deformation is guaranteed. And then when it deforms back to their original shapes, their initial energy and the final energy would match up again. But in the middle here, at this situation, energy is not conserved in the middle. It is conserved only in the very beginning and the very end. And this is a very important thing to note. However, momentum is conserved at any point of the problem. Yeah, at any instant. It works. Okay, good. I hope you understood it well. And that's why let's try to write equations to it. Equations would look something like this. Yeah, let me take conservation of energy. Let me note it like this. P initial. Yeah, this is equal sign. Would write it like this. Yeah, maybe M1 V1. Yeah. Okay, this is just M. This is not M1 V1. It's just M V1 plus MV2. Our mass is the same. Let me look at this. Velocities of the bodies are equal to. Okay, the masses are not said to be different. Yeah, but if the information is not given, we cannot guarantee that masses are the same. It has to be some mass 1. This is some mass 2. Again, mass 1, mass 2, 1, and 2. If it was identical, it would be said that it is identical. If you have watched the previous video, then you would see that in the situations where masses were identical, it was said so. But if it is not said, we have no any guarantee that masses are the same. Okay, this is m1v1 plus m2v2, and then at the middle it is conserved m1v plus m2v. Yeah, and at the end it is also conserved. It is m1v3 plus m2v4. Yeah, right. Good. And let me write conservation of energy somewhere here, maybe. Sum of energies. It is not vector. It is just scalar. There is no any arrow up. So conservation of energy would be only in the very beginning and at the very end. So it would look something like this. m1v1 squared divided by 2 plus m2v2 squared divided by 2. And then kinetic energies at the end would be just m1v3 squared divided by 2 and plus m2v4 squared divided by 2. Now, common factor 2, 2, 2, 2. Yeah? Okay, good, good. At the middle, the energy is not conserved at the middle because there is some deformation and then it deformates back. Yeah? Okay. Let's see what we can do with it, and I have some idea. Let's first take this one and this one. Yeah, let's just not take into account the middle one. Let's right now concentrate on those things. Okay, what I can do is to take common mass and collect them to one side. So it would be something like this. M1 V1, it would, yeah, I move M1 V3 here, so it would be minus M1 V3. M2 V4 stays there, V4, but M2 V2 goes there, and then it would be M2 V2. Okay, good. And as you can see, we can take M1 as a common factor outside of the brackets. It would be like this. This would be M2 as a common factor. It would be V4 minus V2. Okay, and then if I find the relation, the ratio between M1 and M2, it would be something like V4 minus V2, and at the bottom, V1 minus V3. Good. We have found the ratio between masses. Okay, why did I do it? Because I can do it again with conservation of energy as well. Yeah, maybe I would take the meaning of this problem even lower. Right now, we are not interested in that. As you can see, we can do the very same thing. I can collect M1 V1 squared, here M1 V3 squared. At that side, it would be the very same thing, V4 squared minus M2 V2 squared. And we can take M1 as a common factor. It would be V2 minus V3. And here we would have common factor M2. It would be V4 squared minus V2 squared. And then the ratios between masses would be something like this. M1, M2 equals V4 squared minus V2 squared. And at the bottom, it would be V1 squared minus V3 squared. Okay, as you can see, we have found the meaning, the ratio of the masses between each other. And it is also here. We have two meanings of it. One of them comes from conservation of energy. One of them comes from the conservation of momentum. And then we can take the meaning of both of them, yeah, and equalify between each other. Then at the middle, yeah, maybe let's write it here. It would look something like this. At the bottom, okay, we have here V4 minus V2 divided by V1 minus V3, if I'm not mistaken. Yeah. It equals to another ratio of masses, which is this one. As you can see, okay, let me write it here so you don't get distracted. V4 minus V2. This is squared. This is V1 squared minus V3 squared. Maybe, just maybe, let's take it a little bit higher. Maybe here. Yeah. Like this. Yeah. Or maybe here. Yeah. Let me take it a little bit lower because I have some idea to implement a little bit later. Okay, right now what we should do is something like this. You can see that this one is a squared minus b squared. You know this formula, basic identities. And then we would have something like this. It would be v4 minus v2. This is v1 minus v3. It would be in the brackets v4 minus v2 and v4 plus v2. I hope you know it, yeah? It comes from maths, and it would be v1 minus v3. This is v1 squared, v1 plus v3. Okay, as you can see we have, if we take these things into brackets, that's not a problem. You can see that we can cancel these out and cancel these out. And then we are left with 1 in here and these things. Okay, we can move that bottom thing in the bottom, which is this one, and move it to that side. It would be v1 plus v3 equals to v4 plus v2. Okay, good. I like it. But also what we can continue is something like this, v3 minus v4. It would be v2 minus v1. Okay. Yeah. Okay. Or instead we can write it as v1 minus v2 equals v4 minus v3. Yeah. Okay. Let's keep this thing. This is very important. This thing is very important. Okay. The next idea that I'm going to implement right now, I'm going to find the ratio of the masses in two situations. Let me take something thicker. Right now, let me take two colors, which is violet and green. I would take the meaning of this part, and then I'm going to take the meaning of this part. Okay, that's why, yeah, let me write it as maybe 1. Let me write it as maybe 2. Yeah, and it would be something like this. Okay, for 1, yeah, let's write it here, maybe. Okay, yep. I think that I should move it, maybe, yeah, let's take it, maybe put, oops. Let's move it probably here. Let's move this thing maybe a little bit closer, so we have some space to write. Yeah, okay. Right now, let's concentrate on this violet part. Let's do very same thing. Let's do very same thing as we did in the beginning. It would be, oops, yeah. This is M1. I hope that you understand what it's going to be. We collect M1s outside, and then, yeah, but, okay, just forget about this part. We're not interested in this part right now. We're interested only on this, right? And then I would do very same thing. M1 V1 minus M1 V. There we have M2 V2. Yeah, at that side. No, M2 V just, yeah. Minus M2 V2. And then common factor M1 comes out. It would be minus V. This would be M2 outside. V minus V2. Okay. Right now, let's take 2. Let's take 2. I would write it here. The very same principle. But right now, let's take and let's cancel this out. We're not interested in this. We're interested only on this. Let's collect M1s again to one side. It would look like this. M1 V minus M1 V3. That side would be M2 V4 minus M2 V. And then we collect M1s, V minus V3. This would be M2 V4 minus V. Right? Okay. Right now, let's take these two things. Let's take this thing. And let's take this thing and divide them to each other. And then you can see something very interesting. If we divide it, mass 2, mass 2, mass 1, mass 1, they cancel each other out, and then we would have something like this. It would be V1 minus V, here V4 minus V. Yeah, if you ask me why, I just take it and multiply it to here. I take it, multiply it to here. Basic proportions. You basically know that, yeah? Okay, and here we would have V minus V2 as the main part, and also V minus V3. Okay, I hope that I didn't do any mistakes. And yeah, let's continue and open this up. We would have here below V1 V4 minus V1 V minus V V4 and plus V squared, right? Okay, good. Here at that side, we would have V squared minus V V3 minus V2V plus V2 V3. Okay, good. As you can see, we have at both sides the very same positive V squared. That's why we can cancel that out. And here we can do something very interesting. As you can see, we need the meaning of V4. Let's take anything. In fact, it's not exactly V4, but I would take V4, yeah, to work with. You can do anything. It works, still works. Okay, here we would have something like this. Oops. If I take it, yeah, let's do it step by step so you don't get distracted. I don't want you to get distracted. It would be VV4. Let's move this thing to other side, and then it would become positive. And then here we would have something like, yeah, this thing will become positive. It would be VV1 minus VV3 minus V2V plus V2V3. Okay, good. Let's take out V4 as a common factor. It would be V1 minus V. Here we would have V1 V minus V V3. Yeah, and minus V2V plus V2 V3. Okay, can we do something about it? Can we do something about it? Let me see. Well, not yet. Maybe not yet. Okay, V4 would have the meaning of everything here and divided by this thing, right? Okay, like this. Okay, this is the meaning of V4. We can do anything. Yeah, it does not have to be V4, but I chose V4. Okay, this is the meaning of V4, but there is one thing that we didn't use is this one. Yeah, we have found that V1 minus V2 equals to V4 minus V3. And right now we can take the meaning of V4 and put it here. Yeah, that's why I don't want to write it totally. Just let me take it, put it maybe here. maybe like this. Yeah, let me delete off all of it. Yeah, let me take it, put it here maybe. Oops. Yeah, also we have minus v3. Oops, sorry. Yeah, like this. I just took the meaning of v4, which is from here, and I put it inside of that thing. Okay, and to make it common factor, then it would be something like that. Yeah, let me continue with, I don't know, red, or what would be convenient. Okay, let's continue with blue maybe. v1 minus v2. This thing would be v1 v minus v v3 minus v2 v plus v2 v3. Also, if we give that thing to multiply, yeah, then it would be minus v1 v3, and the minus and minus gives us plus. It would be plus v3, right? Yeah, and everything below would be this thing, v1 minus v. Okay, and very interesting thing, this is positive vv3, this is negative vv3, right? And right now, let's continue. This is v1 v2, and then here, what can we do? We can take out some common factors maybe, and as you can see, maybe, just maybe, we can do what? Oh, yeah, I think that I see it. Okay, let's take v1s, yeah, this v1, and take them out as a common factor. Okay, let's see, let's try. Inside we would have v minus v3, yeah? Okay. Here what we have, here we have plus, right? Let's bring out v2, yeah, v2 out, and then we would have something like this, v2 and v3 stays inside, positive and negative v. Okay, this thing is v1 minus v, and yeah, I think that I see it. We can do what? We can take this minus, as you can see, this is v minus v3. This is v3 minus v. We can take this minus, bring it out, and yeah, this would be plus, but this thing has to be minus. Yeah, the meaning keeps, because if it was minus, if it was plus, if we open that, then it would be minus. This would be minus as well. It still works. Yeah. Yeah. Oh, yeah. Let's try it. This thing has to be minus. v2 has to be minus. This thing has to be, yeah, v and v3 has to change their meanings. v3 would be minus, and v has to be positive. Yeah, like this. In this case, the very same meaning keeps. Yeah, this thing is still minus, and minus v2 and v3 gives us positive. Yeah, meaning is kept. It's good. And as you can see, these two, yeah, let me even show you. These two are the same. That's why we can take it out, and then right now we would have something like this, v minus v3, but inside of the brackets we have what? v1 minus v2. Yeah, below we would have still that v1 minus v2. Yeah, and everything, yeah, let me take it, and everything here is equal to this thing, right? Okay, yeah, I'm sorry. This is v1 minus v. And you can see that this thing can be cancelled out, the very same thing. And we can move that v1 minus v to that side. It would be what? v1 minus v. And yes, we right now found the meaning of v3. We can move, we can move v3 here and everything to that side, and then we'd have the answer of the v3. v3 would be what? Minus v becomes positive v. We already have 1v here. That's why it would be 2v, and v1 becomes negative. Yeah, this would be negative. Yeah, that's the very meaning of the v3. Yes. That's pretty good. We have found the meaning of the v3, and okay, and maybe, just maybe, we can put it. Yeah, we can put it inside here, and then we would find the meaning of v4. Yeah, because we are asked here, where is it, the problem statement? Okay, what were the velocities after the collision if they are moving along the same straight line with speeds v1 and v2? So what are the velocities? Yeah, so the velocity 3 and velocity 4. We can take this meaning of v3, yeah, this one, and paste it inside here. And then, yeah, every problem is solved, I believe. Let's do it. Let's keep doing it. So it would be, let's write with red, so it would be better visibly. So it would be still v1 minus v2, and here we would have v4. The meaning of v4 is not still found, but the meaning of v3 is this one, 2v minus v1. 2v minus v1. Yeah, and if I open the brackets, this thing stays minus, but this thing becomes positive. Yeah, And you can see in both sides we have that positive V1. That's why those can be cancelled out. Yeah. And then the meaning of the V4 is found as well. So it would be 2V positive, yeah, because we move this thing that side, and minus V2, then it would be V4. Yeah, we have found the meaning of V4. This is the very meaning of V4 in our case. Okay, we have found the meanings of both V3 and V4. Good. I hope everything was clear to you. It's not much of a hard thing. In fact, yeah, let me take it out and explain from the very beginning. We used conservation of momentum, right? And it is conserved at any part. In the very beginning, in the middle, at the end, it is conserved. For conservation of energy, it is conserved only in the very beginning and at the very end, not in the middle because there is deformation. Yeah. And then what we did, we took the meanings of this one and this one. As we know that these whole things are equal to each other, that's why we can take only this, and then we moved the masses, the same masses to one side, and we have found the ratio in conservation of momentum. Then we have found the very same thing from conservation of energy, the same masses to the same side, common factor gets out, and the ratio of masses. Yeah, and then what we did is we made those two things equal because this is ratio of masses, this is also ratio of masses, and what we did is this thing. Yeah, well, this thing equals to this thing. It is here. You can see it. Yeah, as you can see, we can open this thing with basic identity formulas. This thing cancels. Only this thing is left, this thing is left. Here we have just one, that's why we can move it to this side. And you can see that we have this meaning. We just moved this V3 to this side and V2 to this side. Yeah, so we left this formula here. We didn't use it for some time because we were interested in this thing. What is this? We took, if these three situations are equal to each other, then we took this part as the first situation and then this part as a second situation. Yeah. And then this is the first one. We moved the very same principle, moved the same masses to the same side. The same principle for the second part. We've divided two equations to each other. Masses get cancelled out, and then this thing moves up, and this thing moves up as well to the other side. And we open the brackets. Everything comes something like this. At the end, we have found the meaning of one of them, of V4 or V3. It does not matter. We can do anything. And as we have found the meaning of V4, we just put it inside of this formula, and everything else is just mass. Yeah. This thing is multiplied to this one, and yeah, we at the end have the entire meaning of V3, and then we take the meaning of V3 and put it here to find the meaning of V4, which is here. Okay, good. Yeah, very interesting problem. It looks easy, but in fact is not hard, to be honest, but it is not very easy as we have expected in the very beginning. But anyway, I hope that it was clear to you. If it was not, please be free to text me and ask some questions. I will try to answer to your questions as much as I can. Thanks for your attention. Goodbye.